Welcome to Walk About the Galaxy, the relentless astronomy podcast. Nice. I kind of feel like it's that kind of mood, too. It's relentless. Where the science is universal, the opinions are personal, and the hosts are restless and relentless. The podcast is relentless.
The hosts are restless.
The hosts are restless. We are Strange, Charm, and Top, the Astroquarks, also known as Josh Caldwell,
Addie Dove,
and Jim Cooney,
coming to you from the Walkabout Studio at the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. Check out our website, newly rescued from the tendrils of hackers, at walkaboutthegalaxy.com, where you can see how to order a Walkabout shirt and support STEM education at the same time. Our stumper today, you know what I discovered recently, you may have noticed, is that it's half as much work for me to just give you each the same stuff.
That's interesting discovery. Did you do some sort of statistical analysis of that?
I did a Bayesian analysis, which we'll come back to later. Okay. Our stumper today is nomenclatural. Okay. Space missions and physics experiments, which we're familiar with in abundance, get names from their mission operators, principal investigators, and so forth. And frequently those names are acronyms. So, for example, we've talked recently about 3 upcoming Venus missions.
Yep.
The 2 NASA upcoming Venus missions are acronymed.
They are.
Veritas, and I'm going to emphasize the words that get the acronym letter. Venus, emissivity, radio, science, INSAR, topography, and spectroscopy. That's 1, Veritas. And Da Vinci Plus, which is Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. Plus, those use the acronym approach. At the same time, ESA has a new mission going to Venus where they did not use the acronym approach. Their mission is just called Envision, which is fine. Although I kind of feel like if you're not going acronym,
you got to tie it in a little bit better to...
Maybe something.
Yeah.
I don't know. Envision is fine.
We have some good names for things in the lab that aren't acronyms.
What's our best the computers. But like experiments, our experiments...
My chamber is called holodeck.
Yeah.
We have warp core and R2-D2.
But in terms of like project type stuff, we're mostly acronyms.
Strata is not an acronym. My Strata projects are not an acronym.
Mm-hmm. Well, you get to name the next planetary mission after this. Which kind of name do you give it? An acronym name or a name?
Oh. This is a different format for a stumper.
Yeah.
I
didn't want to have you say, okay, where is it going? And and then if you're doing an acronym, then you have to sit there.
I like a good acronym, and I am pretty good at making some pretty good acronyms.
What's your favorite acronym that you've come up with yourself?
Pinball is still my favorite acronym.
Which stands for?
Projectiles. And I think the I comes
from the I in projectile.
From the I in projectile. But I think I did a modified. I think I did a modified version sometime that made it work better.
Rants coming.
On board, a lunar lander.
Lunar lander. On board, lunar lander is where you get the ball from. Mm-hmm. Okay, pinball is good because it's an acronym that's word in it.
It's like an onomatopoeia
with
acronym.
What it is. Yeah.
I like those kind the best. So I'm going to do that kind
You'll
of
do
mission.
an acronym for your mission.
So if I do a moon mission, it's just going to be called Moon, but it'll be an acronym.
Figure out.
No, don't do that. That's the worst. Like Psyche mission to Psyche frustrates me.
Well, we ran into problems because we had an experiment called Nano Rocks.
Yes.
Which is not an acronym.
No.
It's a small experiment that involves little tiny particles bumping into each other, so rocks. So that makes sense. And we thought it was cute because it was going up on a platform on the space station, which is called NanoRacks.
Yeah. And it is cute, but it just got confusing.
Super confusing.
I always say the wrong
NanoRack,
thing.
Yeah, it's like a little confusing. How about you, Jim?
I'm going non-acronym.
Non-acronym.
Knew it.
I know. Yeah. Well, look, I really do appreciate a well-crafted acronym.
Mm-hmm.
It's gotten so forced. Everything, all of these big missions, experiments, everything are all... Not all acronyms, but there's so many of them, and they're so forced. And I appreciate ones that are they're nice. I hate acronyms that include more than one letter from a word.
The same word.
Or a random letter from the middle of a word or something.
Yeah.
That's outrageous.
What about the first 2 letters of a word?
No.
Not even?
No.
A lot of missions are names.
Most of the that's what I was thinking. So like Cassini, Europa Clipper,
Galileo.
New Horizons.
Yep, I'm liking those.
names.
Curiosity.
And like a lot of the instruments then have acronyms.
Right.
Or sometimes you do fun things where like the instruments are themed names.
Yeah.
That's a fun thing too.
So yeah, the big NASA missions tend to have non-acronym names. The Discovery level, which are sort of these PI-led sort of $500 million scale missions, which is not that's not a big mission, but it's not at the scale of like Europa Clipper or the Mars rovers. They are more frequently acronymed, and that's, I think, because they're come up with by people like you and me, professors at a, or scientists who like to come up with a clever acronym instead of NASA project managers who are maybe, to their credit, having a bigger picture in mind and not trying to make a sales pitch the same way. So like Messenger at Mercury is a super...
I do hate that acronym.
And OSIRIS-REx is also a very complicated
rough.
one.
Yeah.
So
that one really bothers me because it's just like it doesn't mean anything. Also, like it's a
Messenger.
OSIRIS-REX.
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 It's a forced acronym, and then it doesn't even. To me,
they have arguments that it does mean something.
I guess, but if you have to make arguments that it means something,
right?
Then come on.
Yeah. Okay. Well, today we'll talk about rogue planets.
Acronyms. No, I'm just kidding.
Maybe acronyms may come up in the discussion. We'll see. More stellar remnant collisions and, speaking of Cassini, the odds of life on Enceladus. But first, this episode of Walkabout the Galaxy is brought to you by string theory. Nice. If you hate to be pinned down, try exchanging your point-based view of the world around with a stringy approach that gives you the extra degree of freedom afforded by having an entire dimension to play around with. That's right, with string theory, you can be an open string or a closed loop, and your shakes and wiggles tell the world all about you. As an added bonus, when you move through space, your trajectory is a surface rather than a line, and if you want to get really freaky, get a superstring and a bosonic string and make yourself a heterotic string. Ooh. So whether you're looking to unify all of physics or you're just looking to stretch yourself into some extra dimensions, try string theory. String theory, if it keeps going and going and going.
I think my shakes and wiggles do tell the world a lot about me, even if I'm not in string theory.
Well, maybe you already signed up for string theory.
Maybe. I've heard it sounds like a good workout studio.
Energizer.
Correct.
Energizer.
Also, mini
or
rant.
A good quoting or a good sewing studio. String theory.
String theory is stupidly named.
Oh.
Have I gone on this one before?
I feel like this is a good rant. This is a rant-isode.
I was getting excited about a rant because when you said, okay, rant, string theory is stupid, and then I was getting really
string theory
excited.
Itself is not stupid, but it should be string hypothesis.
Oh, yeah. That's true. You don't have a problem with the string part.
It's just
so frustrating.
It's not a scientific theory.
Right. I mean, in English, hypothesis and theory are roughly synonymous, but in
science,
we make this big thing about how they're not the same thing. Like the theory of evolution by natural selection isn't a guess. It's a guess backed up by hypothesis backed up by a huge amount of data. String theory is, in point of fact, a hypothesis that has not been tested, and therefore we should name it differently. We're not doing ourselves any favors by not,
That's true. That's a good point, and I've never actually thought about it, that particular point.
Right.
Yeah.
Rant concluded.
Do you feel better having gotten that?
A little bit.
Heard that out a little bit?
Yeah.
Okay. Space News, of course, we mentioned this in the last episode. In principle, by the time this episode is out, Virgin Galactic Spaceship 2 will have carried Sir Richard Branson, as well as our friend and colleague Surisha Bandla, into near space or space, depending exactly on how you want to define it, but definitely up above most of the atmosphere.
They're giving them astronaut wings. So.
And they'll be having free fall for a couple of minutes and see a black sky in the middle of the daytime. It'll be a heck of a ride for sure. So that's scheduled for July 11th nominally, and we haven't heard. we're recording this on July 7th. If they were planning, at this point, we know from past experience, we have no inside information about this particular flight at all, but we know from past experience on their processing at this point, things are well on the way for prepping for that flight.
Yeah.
So assuming that all is going well on that, and then shortly afterwards, Blue Origin's New Shepard.
Yeah, they're not racing. Branson isn't racing.
I heard that he said it's not a race. Just coincidentally doing it
really
a week
quick
before.
Turnaround and a week before the other flight.
Yeah. We don't know who the $28 million passenger is.
Still don't know. Still a mystery.
Yeah. And there's 2 weeks. It's 2 weeks from yesterday is when that will be going up.
God.
Yeah. Exciting.
Where's the summer gone?
Yeah. You have an experiment going on the flight after that one, correct?
I do.
With Blue Origin?
With Blue Origin, yeah. The uncrewed flight. Right. No humans, only science.
Right. And then I believe our colleague
and hopefully the one after that as well.
Persay has one on that as well.
It's highly possible.
Yeah. I have speaking of rants.
Ooh, go for it, buddy.
Have either of you
No.
or has either of you seen The Tomorrow War?
I have not. I've seen the trailers and a brief review.
Okay.
And I generally know the premise.
I didn't see it either.
Okay. Well, I'm a little bit. So this is recently out on Amazon, I think, or Netflix.
One of the streaming channels.
It's a sci-fi alien shoot 'em up adventure movie with Chris Pratt. Time travel. So it's got a bunch of elements that I get a kick out of.
Yeah.
I love me some time travel.
Sure. Yeah.
Sure.
I love me, shooting nasty looking aliens.
Sure.
I love it even better if they turn out to be misunderstood. Sort of like Devil in the Dark, Star Trek original series kind of thing going on. So I'm like, okay, I'll go for some guilty. You don't know Devil in the Dark, Star Trek original series? The Horda?
I've seen it, but I don't know.
The Horda with the silicon eggs.
It's the Horda.
And it's a horrible, horrible monster. Then it turns out that, no, actually, it was just a mother protecting its babies.
Yeah.
Anyway, I'm excited about this. I'm thinking guilty pleasure, and I watch it. And then a moment of such supreme stupidity arose.
Only one? I anticipated a lot more.
Well, no. I mean, you give these things, there are certain things you just go with.
Okay.
But this is spoiler alert. Okay. So spoiler alert for our listeners.
I'm okay with that.
And I will post on our Facebook, like, how many minutes into the podcast you can jump forward to skip the spoiler.
How long is this rant going to be?
You got to tell people how far forward they go, right? If you're watching it on YouTube, I'll wave my arms after when I'm done. So people, there's terrible, nasty aliens invade us 30 years in the future, and they're wiping out all of humanity, all of life on Earth.
So they go back to recruit people, bring them forward.
Somehow, magically, in the midst of this invasion, humans managed to create a time travel device that lets people go back 30 years and recruit or draft soldiers to go forward 30 years to beef up the armed forces of the future.
Not just like fight them in the past so that doesn't happen in the future.
Right.
Okay.
You're foreshadowing a little bit part of the rant, but
checks out.
So whatever. You grant that their time travel thing is this 30-year offset. People portal, and it drifts forward 30 years apart. So they're always
it's always a 30-year gap.
It's always a 30-year gap. So you're always going 30 years later into a worse situation in the war in the future.
Got it.
Well, in the future, somebody develops a poison that will kill all the aliens.
Yay.
Sends it back 30 years for it to be mass produced.
Okay.
Then the portal breaks. So the stuff goes back to
present day.
We've got this poison.
Okay.
We know that in like 27 years, aliens are going to be arriving.
Yeah. Right.
We've got this poison. And he's like, okay, we need to mass produce this so that I can now take it 30 years into the future when there are less than 1 million people alive on the planet. And then we can kill the aliens then. And somebody says, we can't. The portal is down. And they're like, that's it. It's all over. We've lost.
All over. Nothing to do about that. Can't let time progress and I'm have other solutions in this 27 years.
No, you have 27 years now to make this stuff and be ready to kill them when they show up before they have killed 99.9% of the human population.
Well,
makes
sense.
But is it
But they're like, oh, shoot, we can't go forward into time to when we've lost 99% of the war and try to kill them then. So we're all we've lost the war.
Yep.
And I had to turn it off. I couldn't watch it. And presumably...
It gets not better after that. I've seen a review and it does not make more sense after that.
Well, I imagine...
They don't make better decisions.
What? You don't, even if the time portal is alive, you don't want to take it forward. You want to use it in 27 years. You've got your own time portal called the natural passage of time that will take you forward in time the amount of time you want to go, which is not 30 years to near the end of the war, but 27 years to the beginning of the frickin' war.
Yeah.
Why aren't you guys screaming with me here?
We didn't see it. I'm worried. I'm only worried about the one of the things they do in all these time things is like different branches of. So maybe like they're worried that if they just wait the 27 years and poison them, that the people in the other time branch are all going to die.
I don't think that
they were not expressing
they never
that
expressed
concern.
Time branch
all those people are dead anyway.
Yeah,
everybody's dead. There's less than 1 million people alive.
Right.
At the time that they want to go to.
Right. But those last 1 million people,
no, you're not.
Are they on
a
different branch than the?
They don't talk about branches. You've been watching too much Loki.
Obviously, it doesn't make any. There's no sense to all of this stuff.
No, of course not.
But the fact that they would go, oh shoot. Now we're screwed. We have no way to kill these aliens.
So I think you need to finish the movie.
I'm not going to finish the movie.
Okay.
You're not going to finish the movie? If not just for the joy of the rants?
Because there's more rants to come.
Oh, God. Okay.
Based on the review I saw.
Some rants.
Which was just like rant, but not in rant form. It was actually pretty fun.
I just need somebody else to watch it up to that point to share my outrage at this particular
I was
point.
already angry from the beginning.
All right.
I'll do it.
I'm waving my hands.
Welcome back.
It was 2 minutes. I got to remember to post that.
That was a long rant.
The rant is over. If you're listening, you have come to the appropriate post-rant stage.
All right. If you want to watch it on mute and just watch Josh get red, it's pretty entertaining on the YouTube. He was quite upset.
Yeah.
I'm too tired to be upset right now. Sorry.
Okay. All right. Well, let's talk about something we're supposed to talk about.
It's rant.
Rogue planets.
Rogue planets.
This was fun. It also has a Star Trek connection. Squire of Gothos.
Doesn't everything have a Star Trek connection? We've talked about rogue planets before.
We have talked about rogue planets.
I'm going to sweep right past that Star Trek reference.
Okay. So what is a rogue planet?
It is a planet that is not tethered to any solar system. It has gone rogue. It's not a prodigal planet. It's a rogue planet.
Right. So rogue planets. Born that way or thrown out?
I don't think it's a Lady Gaga song. So probably they came to be somewhere and then were set off on their path of adventure.
Ejected.
Yep.
Kicked out of the planetary nest.
Jumped out of the planetary nest, maybe.
I mean, it's an interesting thing. We sort of assumed these objects would exist before ever detecting any.
Yeah.
And this current detection is 4 new rogue planets with the Kepler Space Telescope, which is the exoplanet detection telescope, using a very interesting technique, which we'll come back to in a second. But when planetary systems form, you get a big planet, things get gravitationally scattered around and kicked around, and those events, those close encounters, can kick stuff completely out of the stellar system.
When I did a summer REU research experience for undergraduates in Hawaii.
Lucky.
It was pretty great. I worked on doing some Mercury modeling, an N-body integrator.
The computer program.
That did, and doing modeling of some exoplanet systems to see, because you can do modeling of current configurations that we know of and see if there used to be another planet that maybe got kicked out and it rearranged the ones we can see.
It's fun stuff.
It was fun.
I mean, in some sense, we've had a visit from a rogue planet or 2.
Rogue planet.
Tiny ones.
Every time I'm going to do that.
Okay. Oumuamua.
Yeah.
Mm-hmm. And what was the second one called?
Borisov.
Oh, yeah.
Yeah.
And maybe those are planetoids.
Which was, but small objects that formed around some other star and got ejected. And there's no reason why a much larger object can't also get ejected. And so those would be what we call rogue planets.
Rogue planets.
And they're just sort of drifting through space, not near a star, which makes them very, very hard to see.
Yeah.
So and if they're hard to see in visible light, they're hard to see in this detection technique that they used for this thing that I don't actually believe works, but they say it does.
Right.
And I just don't understand how.
So
some of the levels of detail you have to get into processing in order to get this sort of data out just blows my mind.
Yeah. So describe the technique, if you would.
So the technique is called microlensing, using a microlensing technique. And we've talked about microlensing and lensing before.
Normally, think a telescope, you have a really big lens. This time they use a really tiny lens.
There's a little tiny lens, and that helps you see things differently. Now, we've talked about lensing before, typically in context of big cosmological things or galactic things.
Right.
It's the bending, because general relativity says light bends around massive objects because the space is bent.
That it does.
It does do that.
It's not just general relativity saying it.
Right. Light bends around little things, which means that when one thing passes directly in front of another thing, some of that light from the background thing is bent around the foreground thing, and that can cause all kinds of freaky things to happen. But one thing it can cause is the object to appear to brighten temporarily because now you're seeing light that was headed off in other random directions suddenly.
So let's label. So there were a lot of things there. So let's say thing A is a star very far away.
Yeah, very far away.
And let's say thing B is a rogue planet.
Ooh, thing B.
Okay.
Ooh.
So
aliens on thing B.
Here we are at Earth.
Right.
So thing B passes directly in between thing A and the Earth.
Right. Okay. So the light from the star, thing A, is bent around thing B, or a little bit of it is warped. Mm-hmm. And some of the light that was headed off into other regions of space now is bent toward Earth. So now the image of thing A gets brighter temporarily.
Right. Okay. So we're getting all the light that we would normally get from thing A, but then we also get some light that would have missed us.
Right.
That gets bent back towards us.
Right.
And thanks to knowing how general relativity works, you can figure out exactly what that little brightening blip would look like depending on the geometry of this event.
Yeah. So what did they find? I'm excited. You guys read this, and I didn't read this one.
So the thing that boggles my mind about how they found it, before we actually say what they found, is it's this crazy processing technique that they're now doing with this Kepler data. So it's Kepler K2 data, which is already good, useful data, but lower sensitivity and noisier, just because it's the K2 mission was when the cryocoolers or whatever, right? It was in the secondary part of the mission, so it wasn't just good pointing. It was just sort of drifting, and
I think it's a
gyroscope.
One of their reaction wheels for stability.
That's right.
They only had two axes.
It wasn't a thermal thing. It was So they couldn't point it as well, so they were sort of doing these more general looking at things, and so they're not even So, and it's this level of data where it's basically we tried to see if there was noise, and then we sort of crinkled up that noise and pulled it apart, and there was maybe a planet in there. And I'm just how do you even do this?
Are you looking at figure 3 of the paper?
I did look at figure 3 at some point.
So figure 3 is a flow chart of the data processing diagram. And the first step in the upper left corner says 3,752,652 light curves.
Yeah.
And then there are, 20
Several
or 25 flowchart, circles and squares of steps that get performed on the data.
A bunch of them are filtering. So you basically say, remove this noise source. And you say, what would this noise source look like? And you remove that from the data.
Yeah.
And then you look at the light peaks and stuff like that, and then they remove asteroids or other transient things, and then they look for periodicity, and oh my god, there's so many things.
Awesome.
It's insane.
They found
it's not
5 new candidate events.
At the upper left corner, it starts with 3.7 million, and then it winds its way back and forth across this flow chart with, just as Addie was saying, the different. Let's make sure it's not a stellar flare. That gets rid of 700. Let's make sure it's not temporal noise. That gets rid of 500,000. Let's make sure it's not an asteroid or something.
It's a little bit like,
6.
yeah, like we talked about previously, like sort of statistical analyses where you're like looking for statistics in the smiley face arc data. This is different than that. This is like filtering data and pulling out the data. Anyway, they did all this.
They did all that again.
And they have 5 candidates. And one of them corresponds with actually a candidate from a different technique that was used. So they're pretty certain that that's a thing. And then they find 4 of these microlensing rogue planet candidates.
You can do a self-rogue planet.
Self-rogue
planet. Callback.
Yeah.
So,
and they say they're somewhere in the galaxy. Between us and these other stars. So they say they're probably sort of relatively close. It's really hard to tell like how far away they are. But they're looking sort of toward the galactic bulge when they do this. And so they find 4 of these potential planets.
Yeah. And I mean, you gotta love scientists when you see stuff like this, because they're like presented with this, here, do something with this. And they're like, all right, I will do something with this. I'll take your 3.7 million impossible to interpret light curves, and I'm going to put some science on it. Yeah.
Yeah, the amount of work that goes, I mean, like.
And then you discover something pretty incredible.
Yeah.
Right.
Yeah, because it's not just like Kepler tells you, here are 4 planets.
Right.
Like the amount, I mean,
you have found 4 planets.
Yeah, the
Congratulations.
Number of steps between the data that you actually, raw data, and the interpretation of that is insane, the amount of work.
One of the last steps is like detailed vetting. So there were like 12 event candidates, and then the last one was just sort of like, okay, how realistic are these? So like actual human checking.
Right.
But it's pretty cool.
Yeah.
And so they can do they can try to do like some follow up with Kepler or with Herschel is the next telescope that's coming online that will maybe be able to look for candidates for these types of events. So this is a cool process.
Right. I would think that the individual events are not going to read because obviously you rely on this precise lineup and it happens and then it's done.
Yeah.
So it's unlikely to see those 4 rogue planets again. But I guess that finding these 4 tells you something about the distribution or the number of these things.
Right. So even then that becomes a whole separate difficult problem because, as you were saying, it's thing A and thing B. It takes 2 to tango for the gravitational microlensing. Mm-hmm. And so you have to have a really good model for all of your background thing A distributions and where you're looking. So it's not just like you can say, oh, we looked in 1% of the sky and saw 4. Therefore, there are 400. Mm-hmm. It's not as simple an extrapolation as that. So work is ongoing with that, but it's very cool discovery. And the Squire of Gothos is, am I saying, is it the Squire of Gothos? Sounds weird. The Squire of, I think that's what it is.
It is the Squire of Gothos.
Okay. Yeah,
Good
with
job.
Trelane.
Mm-hmm.
He lives on a free-floating planet. He can actually steer his planet around. Ooh,
I want that.
That's clever.
That's a pretty good trick if you can do it.
It's better than the little asteroid Le Petit Prince lived on. The little prince.
Oh, Le Petit Prince, yeah. Okay, so let me that was a planet topic, and I've got planetary trivia.
Woo.
Nice.
Sort of. So we'll use that before we get into our stellar remnant thing. This is we were talking about missions earlier and the Venus missions. Mm-hmm. How many missions have been launched to Venus?
Oh.
Wow.
That's your trivia?
That is remarkable. The vast majority of your trivia questions have a preamble that is considerable.
I know. I was like sort of only partially paying attention.
Blown. You mean you just asked us a question?
that is.
And that is all you did?
Level.
Wow.
Yes. How many missions?
Be a follow-up?
There are some follow-ups and caveats.
Okay. So the question is, how many missions to Venus?
How many missions have been launched to Venus as of today, July 7th, 2021? Include...
It's a good clarifier, because yesterday was a busy day for launching missions to Venus.
Including missions which did something at Venus, but Venus was not their primary destination.
Oh, like bonus 5 flybys and stuff?
For
and
example,
gravity assist count?
Yes. So, but bonus if you want to separate those out. I know both answers. I know the answer without those and with those.
Okay.
And how many of the total because my first question was how many have been launched. How many were at least partially successful of the number that were launched?
How many were what?
At least partially successful. Yeah. Okay. I have some less interesting follow-ups after that, which we'll get to. So take us out of the solar system.
All right.
For a bit.
We'll plunge back in.
We'll plunge back in on our way back to Venus.
That's right.
With a stop by Enceladus.
Okay.
LIGO. That's an acronym.
I don't have a song right now.
But it's not an acronym that's trying to make anything cute or anything. It's just...
No, it's
just trying to be a little shorter than the long name of the thing.
Right.
Yeah. Remember, this is the Gravitational Wave Observatory, LIGO and Virgo, which is the thing in Europe. And we've talked lots about those things, won the Nobel Prize in Physics for all this stuff, and detected all these collisions. Well, one of the things that we hadn't detected, we detected a huge number, I shouldn't say huge number, dozens of black hole collisions between two black holes. A handful of neutron star collisions. But we had yet to discover a black hole neutron star collision until now.
Or like
some
2
time
years ago, probably.
Yeah, I think January 2020 was when these things were discovered.
Okay.
And actually, even though we hadn't seen any before that, we saw two within the span of a week or two.
Surprising.
This was just, we say now just because it was just published at the end of June here in 2021, because it takes a long time to, again,
figure
all this stuff out.
What does their flowchart look like? It's pretty long also.
It has probably also got some crazy things, because make sure it wasn't a truck driving by, make sure it wasn't a truck driving by in another country, but also
it's insane. But it seems like a couple of these events have now been witnessed. This isn't like we talked a little bit about this on another radio show, and we said we were only medium excited by this, just
you
because.
Said you were
I said that. I don't know if you guys were more excited or less. I don't know. Because it's not, it's something that we expected. I mean, if there are black holes out there are neutron stars out there. Obviously, they both exist in binary star systems with each other. It's not surprising that you would have a black hole and a neutron star in some binary system together as well. We just hadn't seen it. And so now we have. The fact that we saw two only a couple weeks apart is very interesting. And
partly the detector had just been upgraded, right? Prior to this, so we were able to see this kind of thing.
That's true, but then we haven't seen any since then.
Suspicious.
Which is interesting. I won't say we haven't seen any since then. Obviously, there may be other things they're working on publishing soon, but but it's interesting. Just because they should be out there, those kinds of systems. Seeing them helps us constrain, the number density of those kinds of systems out there. That's pretty much all we got to say about that. This is not a long topic. It's just it's interesting.
Well, I'm always fascinated, though, by this thing
we
where
can extend.
There are these things like you've never seen them, and then you see a couple.
Right.
And sort of back to back. And how come we're not seeing one every week, basically?
Are we looking every week?
Yeah, I mean, generally these detectors run for months at a time, right, and look for things. I don't think there is a good explanation for why the only two that we've seen came just a couple weeks apart.
Mm-hmm.
Most
Did one affect the other?
Nah, that's almost certainly not true. I will say about the detections, by the way, that one of them is a super robust detection where all three of so LIGO has two observatories, right? One in Louisiana, one in Washington. So one of the detections was seen in both of those and the Virgo one in Europe. One of them was only seen by one of the LIGO guys. The other LIGO piece was down for maintenance. So
they're not up for
and then they did see it in Virgo, but only barely. And so you might... I mean, they've decided it passes all the tests. This was why they published and said it's real. But you could probably make an argument that
I can make lots of arguments.
Yeah.
But in any event,
they'll see more. I mean,
they will definitely see more.
The reason you're not more than medium excited about this is because there's no particular reason not to expect this kind of thing to be happening.
Right. We would expect it to be there.
But we've detected it.
I know, and we've detected. That's actually similar to the Rogue Planet thing. Like, we were sure, I say sure, but, we're pretty sure that they're out there in great numbers.
They're just hard to see.
They're just really hard to see. And then when you actually see them, it's kind of awesome. And this is the same kind of thing. We're pretty sure that there's lots of these or some number of these systems out there.
Right.
I think we'll expect to see once we have because so LIGO is they're always both LIGO, Virgo, and there's a new Japanese and now detector. I forget a Japanese detector, Kagra, I think is what it's called. It's probably the same thing, which has now joined this system of observatories.
Okay.
But they're always constantly upgrading, and I think in the most recent upgrades, we expect to be able to see a fair number of these things, maybe one a month on average.
So a neutron star is like a baby black hole. It's a little bit smaller than a black hole, so the ripples that it produces are not as big as two black holes merging, for example. So it's a weaker signal, right? But there's no particular reason. There's nothing magical about star formation that doesn't allow two stars to form together where one of them is sort of destined to become a black hole and the other a neutron star.
Right. This should be reasonably, we say reasonably common. Of course, in general, large stars are much rarer than small stars, and both neutron stars and black holes are the result of the deaths of very large stars. So it's not like these are littered all over the place in the galaxy.
Well, actually, there's just not as many.
Right. I mean, the binary star systems aren't littered all over the place. But the awesome thing about these gravitational wave detections is most of them are not in our galaxy.
Right.
This thing was something like at least 900 million light years away.
That's a few.
Both of these detections. It's impossible to gauge exactly how far, but that's almost a billion light years at a minimum. That's a fair fraction of the entire radius of the universe. I mean, these are huge distances.
And we're not going to be doing follow-up studies on these black holes.
No, that thing is,
the black hole's probably still there. The neutron star.
The neutron star got entirely munched, right? which is cool and not. It would be cool if there's a little bit left of the neutron star, because when you have that kind of collision, then there's some light, some electromagnetic radiation that's produced by that, and you might be able to see that. If the black hole completely munches the neutron star, there's essentially no light produced by that. And now, in this case, when a thing is a billion light years away, it's going to be next to impossible to see the light from that anyway. But
But so all the fun happened after the neutron star was inside the event horizon. Is that basically what that means, or
it just means there's no
tearing apart
right
of it to leave something outside the event horizon.
Right. Yeah. Everything has gone into the event horizon.
Right. Yeah. Okay. Well, let's zoom back in towards home.
I'm tired of Zoom. I've been zooming all day.
There's been a lot of zooming just in general. Yeah. Let's zoom back in, nevertheless, towards home with a stop at Enceladus, one of our favorite worlds.
It's okay.
This is...
Said it's okay.
It's only okay?
I'm feeling meh about Enceladus today, apparently. Sorry.
Oh. Enceladus is adorable.
I got some gym mez.
I understand. That's the way that goes.
It happens sometimes.
I'll tell you what, though. I'm fired up about Enceladus
today.
Oh, okay.
Good job.
Yeah. Because I hadn't read this article until just recently.
It's a brand new article.
It is a brand new article. It's obviously recently.
Nobody had
but
read
even
it.
more recently than you guys had mentioned it before I saw it. And I thought it was freaking awesome.
Yeah.
It's pretty interesting. So what is it? It is about methane.
Methane.
Do
they say ethane?
They do.
In England?
Ethane also? Methane and ethane? Okay.
I think so.
In Enceladus, can I say Enceladus weird now? No, I can't. Enceladus's plume. So this is actually a statistical study. We love our statistical studies.
We love them.
That is sort of not necessarily pulling apart the plume data itself, but doing a statistical study to say how likely is it that the methane detections and the abundance of methane detected in Enceladus's plume has a biotic source or just an abiotic source. So what are the likely sources of this type of methane?
Right. So Enceladus is a fairly tiny moon. As moons go, and it's barely big enough to be a ball. If it
just hanging on.
Smaller, it would be, a potato.
Yeah.
But it's a ball, and it's very, very
pretty
bright.
ball-shaped.
It's I think it may be the most reflective object in the solar system.
That moon is fresh.
Yeah.
And that's because it's got these geysers that are spewing mostly water out, which a lot of that snows back down on the surface, giving it this nice fresh...
So fresh and so clean.
Fresh, clean, snowy surface. But Cassini flew through those plumes many times at a sniffer and was able to detect methane there, as well as some other more other things in addition to water products. There's mostly water, but other stuff too. So yeah, so where'd that methane come from? We talk about methane in the context of Mars and life.
Yeah, there's often these sort of quasi-detections and debates about
Everybody gets super
detections
excited about methane
of methane on Mars, and it's like, where are the cows?
Right.
There's some good cartoons of that. But a lot of the methane on Mars stuff is still being debated because it's like you occasionally see these little plumes and little puffs of it show up, but it's not clear where that's from. And it's hard to come up with both biotic biology things and abiotic, not life things, mechanisms for both of those.
But in Enceladus, it's really particularly exciting because, Enceladus has an ocean underneath the surface for sure,
Fact.
right?
Yeah, we're essentially positive that those geysers are sourced from a liquid water ocean beneath the surface.
Right. And we see evidence that the bottom of that ocean would have, or there's a fair likelihood that it'd have the kind of things that we have on the bottom of our ocean, which are these like
hydrothermal vents.
Hydrothermal vents, right? That are a source of energy.
Right.
That's where you're getting like the rock that makes up maybe the core of Enceladus interacting with the water and heat and all these tidal forces that Enceladus has.
Right. And there is life on Earth that uses.
Doesn't care about sunlight.
Right, it doesn't care about sunlight. And as a byproduct of its production of internal energy, it produces methane.
That meant.
It does, yeah.
And so this is a very natural biological, avenue to produce methane under the very circumstances that we're seeing on Enceladus, which, again, it doesn't mean that that's the source of methane.
So there are ways to make methane without life.
Right.
Yep.
But it is one of these molecules, sort of like oxygen, where if you see a bunch of it, life is got to be in the candidate list of sources for it.
Yeah, right? One of the ways to make it methane naturally is by water altering rocks, and it's called serpentization. Which I think is a good
doesn't have
name.
anything to do with serpents.
Doesn't have anything to do with serpents. I don't actually. We have to ask Dan where that name came from.
Serpent.
But their statistics show that there's too much methane to just be by that. So it either could or couldn't be life.
Right.
Yay.
50-50?
I don't think it was 50-50. I need to check the statistics, but
So what is this sort of statistical test? I mean, they basically said, okay, let's suppose there's life. Would that produce the methane that we see?
yeah.
Something like that. Yeah.
You're the statistics person.
There's this, it's this weird stuff, Bayesian statistics, which I don't pretend to understand tremendously well.
You need to take that class from the other person on campus who teaches it.
Apparently. But yeah, it's the idea that if you make some assumptions to begin with, then you get some kind of conclusion. If you make different assumptions to begin with, you get different conclusions. I personally don't put a lot of stock into the Bayesian analysis of this, but I think it's...
So, let's put it this way. One of their possible outcomes of this analysis could have been this is inconsistent with our assumptions about what life would be.
Right.
Yeah.
And that
did not happen.
Right.
Yes.
That is important.
And that's sort of the way I think to frame these results.
I like that.
That if you put in all your sort of reasonable assumptions, what comes out of it? And the answer could have been something that doesn't look anything like this.
Right.
Sure.
But that isn't the answer that came out. The answer was it could be this.
Right.
Yeah.
Right.
It could also be that there's lots of organics from like original cometary delivery and that's being processed and decaying sort of in the interior, and that is being exhumed. And in which case it would again be not life. Yeah. But it would mean it would be very habitable to life. Right? Because those types of processes mean it's a very sort of habitable environment. So it's still like, yay, life-y stuff.
Mm-hmm.
So the co-lead author, Régis Ferrier, said, sort of in summary, biological methanogenesis, formation of methane, is compatible with the data.
What?
Nice.
In other words, we can't discard the life hypothesis as being highly improbable unless you decide a priori life is improbable on Enceladus. But
as we
based
know,
on the data,
life finds a way.
Life finds a way.
So to reject the life hypothesis, we need to go back to Enceladus.
I mean,
Agreed.
obs.
Let's go.
Yeah. All right. Well,
Great.
where we are going before we go to Enceladus is Venus.
Okay.
And even though we've only been to Enceladus with one mission,
Yeah.
although we visited it several times in that one mission, we have been to Venus more than one mission.
Oh, wait a spoiler.
I was going to guess more than
5 seconds.
Oh.
How many times have we launched a mission to Venus? How many of those for bonus points were just passing by Venus on the way to someplace else? And how many total were at least partially successful?
Oh, I have less idea than you, so I'm going to go first.
Okay.
Oh.
Because I know generally less about this kind of thing. I'm going to say 15 missions have been launched
Okay.
to Venus, that 6 of them were Venus-specific missions, and that 4 of those were successful.
Okay. So your contention is that there have only been 4 dedicated Venus missions that were at least partially successful.
That's right.
Okay.
I'm a little bit embarrassed for you right now. So.
Fair. That's fair. That's fair.
There are like 3 operational right now, or
Yeah.
very recent past.
Oh, I forgot about those.
Yeah, you're thinking all old missions.
Yeah, I was thinking
But
about the,
even
I was
so,
thinking about
okay,
the Venera
so-
ones.
So,
Anyway,
Addie,
yeah.
what do you think?
I don't hate the 15 number, but I think I'm going to say a little bit higher. So I'm going to say 22 because I like that number.
Uh-huh.
So 22 missions that have launched toward Venus.
Okay.
I think that there have been 13 Venus missions.
22 total, 13 dedicated.
Yeah.
Okay, and how many successful?
7.
Okay. I'm going to blow your minds.
It's going to be way higher.
It is way
Because
higher.
we launch a lot of things that go.
A few guys weren't around in the 60s when
I
things were
wasn't.
just going left and right.
But mostly toward Venus.
Yeah, well,
Okay.
left
Right.
to Venus, right to Mars.
Yeah, sure.
The total number, including en route missions, 46.
wow.
Only 6 en route. So that is Galileo, Cassini, both did Venus flybys.
40 missions have gone to Venus?
40 dedicated missions. Now, some of them were flyby missions, but Venus was the target.
Wow.
So they flew by, and that was the end of it. Those were in the early days.
I said 6?
Yeah.
Terrible.
6 with a success of 4. Of those 40,
Uh-huh.
sorry, of the 46, 30 were at least partially successful. Most of them, almost all of them were successful. A few of them were like mostly successful or partial success.
30.
But you're forgetting about, so there was like half a dozen or more Venera missions.
I was trying to remember how many Venera there were.
Yeah.
There were a bunch of Venera missions.
Sounds like a disease.
There was Magellan,
Yeah.
Okay.
Pioneer Venus. There's Venus Express. There's Akutsake.
Yeah. I
now.
knew those 3,
On the
4.
flyby route, you have Parker Solar Probe did Venus stuff, and Messenger also did stuff.
That
on its
Colombo
way.
just did. Did you count that?
I counted them all,
Okay.
so definitely.
I don't count those as but
They're on the way. I told you the on the way missions.
Okay.
There were 6 on the way missions.
Okay. Oh, that's the on the way missions.
Yeah,
Okay.
yeah.
Okay. Follow it.
Here's your follow-up bonus ones. What space agency, National Space Agency, is got the next proposed launch to Venus? Space mission launch to Venus.
India.
Russia?
Jim is right.
What?
Yes, I
know.
redeemed myself.
Where did you pull that one out?
I
of?
can't
know.
fully redeem myself
Yeah.
because my first answer was
Now,
so bad. But
it's not yet like fully funded, committed, but they're talking about a mission called Shukrayan 1 with a 24-26
Wow.
launch date. Orbiter and a balloon. Veritas from NASA, which we were talking about earlier, in 2028 is next. Rocket Lab, as a private entity, has talked about maybe sending something to Venus
yeah,
in
that's
this
weird.
decade. And finally, I just had to mention when I was looking up Venus missions, a concept mission family that is not a proposal or anything like that, which is an acronym. And the acronym is HAVOC, HAVOC.
ooh, I like that. If it stands for anything good.
It stands for High Altitude
Venus
Operational Concept. So at least it's the first letter only and all the first letters, which would have airships ultimately with people on board.
Would they wreak havoc?
They might wreak havoc.
Venusian system?
And let slip something. The airship would be 129 meters long, 34 meters tall, hanging out in the atmosphere of Venus at an altitude of 55 kilometers, where the ambient temperature is an ideal 81 Fahrenheit or 27 Celsius.
A little warm.
And the ambient pressure is a half a bar, but because the gravity is a little bit less, the density is higher than what you would expect. But the cool thing is because the air there is CO2...
Cloud City.
Breathable air is less dense, and that is then what provides the buoyancy for your airship. So you don't need here we need bags of hydrogen or helium. There you just need air. And that keeps you afloat.
Right.
Yeah.
Air is hydrogen. Actually, I'm just kidding.
Okay.
You just need nitrogen?
Oxygen and nitrogen. Yeah, just breathable air.
Right.
Breathable air.
It is Cloud City.
Your
habitable environment doubles as your buoyant.
Right. Now you got to do something with scrubbing or cleaning or whatever. But yeah.
Always do.
Yeah. So
I would go there.
That would be cool. That'd be a fun vacation.
Hell yeah.
Well, while it may have felt like wandering through interstellar space on a rogue planet, it was just another episode of Walkabout the Galaxy. I was still with it. Give us 5 stars and we'll give you the universe. That's going to be our new trademark tagline.
Okay, I like it.
Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel, where you can see most of our episodes, some of our bloopers, and all of our music videos, and me waving after the spoiler. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At @walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Darusik. Production assistance is provided by Diego Rodriguez. Thanks to our listeners in India and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
And I'm Jim Cooney.
We're the Astroquarks signing off until the next episode of Walkabout the Galaxy. Rogue planets.
Rogue planets.